All right, let's start. Welcome to the DDPS seminar today. Before we introduce today's speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless it is urgent so that our speaker can talk without unnecessary interruptions. That way, we all can enjoy and focus on the talk. Second, no classified discussion is allowed. Finally, the talk today will be recorded. So if you have questions, it is encouraged to use the chat room, but if you like to address the question right away, you can unmute yourself and ask questions. All right, that's about it. Now let me introduce our speaker. I'm very honored to host today's speaker, Professor Alfio Quattroni. He is Professor Emeritus at EPFL at Switzerland, and now he's also a professor in numerical analysis department at the Politec di Milano in Italy. He is the author of 25 books, editor of 12 books, author of about 400 papers, and editor-in-chief of 2 book series published by Springer. He is the recipient of numerous prizes from Euler Prize in 2015 to Galileo Galilei International Prize for Mathematics in 2015 and many more. He is also a member of well-known organizations such as the Italian Academy of Science, member of Academia Europaea, member of the Lisbon Academy of Science, fellow of the European Academy of Sciences, and Science Fellow, and many more. And his research interest focuses on mathematical modeling, numerical analysis, scientific computing with application to fluid mechanics, geophysics, medicine, and the improvement of sports performance. His research, for example, has carried out the mathematical simulation for the optimization of performance of the Alinghi yacht, the winner of 2 editions in 2003 and 2007 of the America's Cup. Today, he will present the mathematical heart, a computational model for the simulation of the heart function. Now, let me pass the baton to Professor Quattroni. Alfio, it's all yours.
Thank you very much. I am facing a little problem. I'm really sorry. I can't see the presentation anymore, so please be patient for 1 minute. I try to rejoin the meeting. Really sorry.
Oh, no problem. Okay, go ahead.
Let me see if I can. One meeting in progress, so what should I do here? Really sorry for that. So good morning. It's evening here in Europe, but it's morning on the West Coast. So thank you very much for this invitation. And this is the title of my talk. And as you see, it has to see with the a mathematical and a numerical model for the heart, actually, to simulate the heart function. So I'd like to start by acknowledging the contribution of many junior and senior people, senior collaborators, almost all of them from Milano. And I would also like to thank the collaboration from many medical doctors from different hospitals and different countries. Of course, this is a teamwork. Let me just say very few words about heart physiology. I think you all know what is the heart. You know that the heart has 4 chambers, 2 atria and 2 ventricles. It receives the blood, the venous blood, from the vena cava, inferior and superior vena cava, and it ejects blood into the aorta, the ascending aorta, and enriches all the billions of cells that are making our body say. There is one effect, which is the one of the mechanical pump. It is a mechanical pump, actually, with compress and relaxes. It compresses in the so-called diastolic phase. It relaxes in the systolic phase, and it relaxes in the diastolic phase. The venous blood is sent to the lungs for releasing the CO2 and absorbing oxygen, and then it gets back to the upper part of the heart. Of course, the heart beats because there is the electrical field, which is activating the heart beating. And there is a sparkling effect that is originating the sinoatrial node in the upper part of the right atrium. And then an electrical field is generated. It propagates through the upper part of the heart, on the two atria, and then it reaches this new node, which is the atrioventricular node, and from there, through a very sophisticated set of networks, say, it reaches all the cells of our myocardium. So the idea here is to try to simulate all these processes. So the electrical process, the mechanical process of contraction and deformation, the fluid dynamical process, because there is blood inside the chambers, and then the opening and closing of the valves, and of course the connection with the external circulation. So this is the idea. This is the agenda, say. And as you know, I will not insist on that, but as you know, when you want to go to the numerical simulation, you actually need to create a geometric model and then a mesh or a grid, say. Now, the geometrical model, you can get it from real patients using CT scan or MRI, or you can take it from Atlas, or you can take from CAD solid models, like the one that you see here in the middle, the zygote, the called zygote solid 3D heart, human heart. Now, here is the reproduction, so the solid model, and you see in particular the grid in the myocardium. This is just a detail of the grid in the myocardium. This is the finest grid that we'll be using. We use 60 million of hexahedra in the myocardium, and this grid will be useful to simulate the electrophysiology, in particular the electrical propagation in the myocardium, as well as the deformation of the myocardium. We need, however, a second grid, which is the one that we use in the ventricles and in the atria, and this is the one that we'll be using for simulating the fluid dynamical processes. So this is just a preview of what we'll be using later on. So the very first step when you try to face this issue of creating a global heart model is to go and deal with the single, we call them core cardiac models. And they include the electrophysiology, the active mechanics, at the cell level, the passive mechanics, at the organ level, the fluid dynamics, the valves motion, and the perfusion of the myocardium through the coronaries. So let me start with electrophysiology model. Of course, I will have no time to derive the model here, but if you are interested, of course, there are plenty of references. We also wrote a book a couple of years ago with Cambridge University Press on modeling the heart. But let me just go to the equations, and I will do the same also for the other core models. So the equation of the electrical propagation is based on either the monodomain equation or the bidomain equation. The monodomain is simpler. It's the one that you see reported here, and it's you see a partial differential equation that depends on space and time. It's say an elliptic equation with a reaction term, which is a nonlinear reaction term. So in the elliptic component, you have U, which is the transmembrane potential, the difference between the potential, the extra potential, the interpotential in the cells, and then you have the an extra term which accounts for the ionic activity. The ionic activity is described by this set of ordinary differential equations. So U is the transmembrane cardiac potential. W is the set of the ionic variables. This is the conductivity tensor that will play a very important role because it, of course, it accounts for the heterogeneity of the muscular structure, the structure of the myocardium. And then you have the transmembrane capacitance. You have the external applied current, and so on and so forth. Now, there are many different models that can be used to describe the ionic activity. Here are some important names, say the Aleph-Pamphilov, the Courtemanche, the Fabry and Severi, the Tentashev-Pamphilov. that we'll be using for the atria. Otherwise, we have the Bueno Rovio, the Tornector Rigo Soera Rudi, or the Bartolucci Passini Severi for the ventricles. So these models very often are experimental models, are phenomenological models. And of course, they have to be tuned to the specific application that you have in mind. Now, at the cell level, at every heartbeat, so a heartbeat takes place over, say, 1 second or less than 1 second. This, of course, depends on individuals. Has this typical structure. So the potential, which is called the action potential, moves from a resting phase to a short repolarization, and then, to a depolarization, which is followed by a short phase of repolarization. Then there is a kind of flat area, which is called the plateau, and then the complete repolarization, and it goes back to the resting phase. And this occurs for the first 400 milliseconds, about half of the heartbeat, say. And what we see here is the membrane of the cell, and you see the channels that open and close, and they allow the ions to move forward and backward, and this is what creates the difference in the potential, say. This is just one simulation. You see one heart, which is based on the zygote CAD model, and here you see the potential that propagates. You see two different views. The left one is from the pericardium, which is the external surface of the heart, and the right one is a cross-sectional view, say. Here you have a millivol. You typically go from -80 to say 40. So this is the solution of the previous electrophysiology problem, say, one example. And this is basically the same solution, but you have a different vision, different view. You see on the left the activation map, and you see the time at which every single, say, cell in the myocardium has been activated electrically. On the right-hand side, you see the activation front that propagates from the sinoatrial node to the atria first, and then down to the ventricles. Of course, you can use this type of simulation for clinical applications. Here is just one snapshot. We are trying to consider here a heart that is affected by a problem of rhythm. You have a ventricular arrhythmia, which is a kind of irregular propagation of the electric potential in the heart. And one important issue here is to identify what are called in the clinical practice biomarkers, and these are lines of areas of low conduction. There are lines of blocks. There are zones of late activation, and it's important to try to identify those kind of pathological biomarkers, because once you have them identified, then doctors, arrhythmologists, can try to operate what they call an ablation. So they just burn specific points in order to restore, hopefully, a healthy and physiological rhythm. Now, here, mathematics can help, numerical simulation can help, trying to identify by numerical simulation this very complex pattern of electrical propagation and those specific points, and try to suggest the doctors where to ablate, and ideally to solve an optimal design problem, find the optimal places in order to, say, optimize the time of ablation, and also optimizing the efficacy of ablation. Of course, this is work in progress, but I think there is plenty of room for great improvement, and to show that this is really very, very, very effective type of help that you can provide the doctors. Now, if you try to set up a mathematical model, you have to face the issue of the data. And data are the geometrical data. I mentioned that before when I say that you have to reconstruct the geometry and, of course, to create a grid. But there are also many other data which are, characterizing the specific art. One of those data are the fibers, the distribution of the fibers and the collagen sheet. Now, the fibers, the muscle fibers, are very important in the model because they enter at two different sides. First of all, they are useful to characterize the conductivity tensor in the monodomain or the bidomain model, the one that allowed to reconstruct the propagating potential, say. And the second one is that when you solve the mechanical problem, you want to compute the deformation of the heart, well, you will end up with typically a Lagrange representation of the displacement, and then you need to introduce, and I will come back to that, in particular the Piola-Kirchhoff, and the Piola-Kirchhoff will depend on the fiber distribution. So reconstructing the fibers is very important, and typically fibers are not really ready to be used. How can you get them? You can get them by imaging techniques like DT-MRI, diffusion tensor MRI. Well, first of all, they are not really available in the clinical practice every day in all possible hospitals, and in general, they're very noisy. You can get them from Atlas. Of course, those are not patient-specific, but you need a very complex vegetation algorithms. Or you can use a purely based numerical method. It's called rule-based numerical method, right? And you compute kind of surrogate of myofibers. And let me say a couple of words on that. Rule-based methods exploit information from histology or from diffusion tensor MRI observations. They compute potentials, two types of potentials. The first one is associated with the transmural distance, and the second one is called the normal distance, which is indeed the apex to base distance. So you solve basically, as you see, Laplace equations to compute those potentials. Thanks to those Laplace equations, you can introduce a new frame of reference. And this frame of reference is the one that is around with the fibers, with the normal duration of the fibers, and the sheets, which are the collagen sheets, by rotating the axis. When you have this type of solution, here you see the way you proceed. You first of all you have to label the different components of the heart, the different surfaces. Then you compute the transmural distance by solving those, say, elliptic equations. You compute the normal distance. You compute the gradient, and then you introduce the local coordinate, and you end up hopefully with the fibers. You see them here on the left-hand side, and you see them on the right-hand side. So this is a kind of pre-processing in order to recompute, in order to, say, obtain the fiber distribution. This is done for the two atria together. This is the first time, as far as we know, that this has been done for the two atria together. And then we patch them with the two ventricles, and you end up with the global reconstruction of the fibers. What you see here is a posterior view and an anterior view, and you see different colors. You often red, which refer to the fiber distribution of the epicardium. The epicardium is the external surface of the heart, and then you have the blue, which is the endocardium. And of course, transmurally, you have a variation of those fibers. So this is a preliminary computation, and in order to fit both the electrophysiology model and the mechanical model. Now, let me say a few words on the mechanical model. We use the classical Lagrangian formulation. So we introduce the displacement from a reference configuration. This is a kind of idealized ventricle to a current configuration. We introduce the displacement. We introduce the deformation tensor, F. We introduce the Piola-Kirchhoff stress tensor, which is the derivative of a strain energy function with respect to the deformation tensor. And of course, you have to make assumptions on the nature of the tissue. So we are assuming here that the material is hyperelastic. So the passive elastic properties depend on a strain energy function, and it's incompressible because it's mainly or mostly, say, composed of waters or blood, say. So it's indeed very similar to a fluid, say, in terms of behavior. And here, I will not have the time to elaborate on that, but we use two different strain energies. One is the Guccione energy, and the other is the Olzaphen and Dogden energy. And we'll be using both of them. Then the point is that you have to see how to generate the active force. So what is the active force? The active force is the one that is generated at the myocells level, the myocardial filament, right? And you have to assume that to be, say, similar to a unidimensional object. And of course, you want to produce the force that is due to, you want to compute the force that is due to the presence of the electrical field. And this force will allow this cardiomyofilament to stretch and to relax. So you have different type of models to do that. One is based on the so-called active stress. The other one is based on so-called active strain. And they amount to use a different type of splitting of the deformation gradient, say. So you have the state variables that describe, according to different models, the status of the cardiomyofilament. And then once you have computed those state variables, you feed the passive mechanics component of the elastic model, say. Here you use the classical elastodynamics equations, where you have the second derivative in time of the displacement, you have the divergence of the Piola-Kirchhoff stress, and you have non-trivial, I would say, canonical boundary conditions on the surfaces. And here the surfaces are the epicardium, the external surface, the endocardium, which is the internal surface, and then you have this basal surface, which is the upper surface in this ventricle cell. So this is the mechanical model, which accounts for both the active and so-called, say, passive components. And now you want to couple together the active and passive mechanics with the electrical potential propagation, with the ionic activity at the cell level, and with the mechanical activation at the cardiomyofilament. So this is a coupled system, and every block here is coupled to the other blocks, and they exchange important information. So the active and passive mechanics passes strains to the electrical potential propagation. This one communicates with the ionic activity by exchanging the potential and receiving the ionic current. The ionic activity, the model for the ionic activity, passes the calcium concentration to the mechanical activation, and this passes, say, the active stress to the active and passive mechanics. And since here you are deforming the solid part, you are changing the geometry, and you have to update the new geometry when you consider the mechanical activation. So as you can guess, those are nonlinear problems, and they're fully coupled. Now, this is the global model, when you have the electrophysiology, the activation, and the mechanics all together, say. And when you see here are just snapshots of the solution. You see the activation time, you see the electric potential at a given time, and you see the displacement, again, at a given time. So the point is that heart is not isolated from the rest of the body, from the rest of the circulation. So how do I account for the rest of the circulation? Here you have many different possibilities. One possibility would be to use, say, brute force, using fluid dynamics based on Navier-Stokes equation on the whole external circulation, which is barely impossible. You have billions of small capillaries and hundreds of large arteries, just to say what you have to be, what you have to face. So typically use reuse models, and this is one of those that we are actually using, and this is a zero-dimensional model. 0D means that there is no space dimension any longer. We only have systems of ordinary differential equations. So you have a block of equations that describe the volumes, the change of volumes in atrial and ventricles, then a block of equations that describe the change of pressures in atrial ventricle, systemic and pulmonary circulation, and then another one that describes the flow rate. And then, of course, you have to couple them with the three-dimensional model that we have seen before. So this is a critical issue, indeed. You have to find the proper interface conditions in order to be as conservative as possible, say, because, I mean, this is a whole system, and they're just for computational convenience splitting it into two components, one which is described by three-dimensional model, and the other one which is described by a system of order differential equations. So this is just one example of a heart deformation. You have the two ventricles, and here they are contracting and relaxing. And to get this simulation, we have to solve the electromechanical coupled model that we have seen before. This is the same type of simulation. Now you have two ventricles. What you see here, what you can appreciate here, is the contraction of the fibers along the heartbeat. And also on the right picture, you also see the calcium concentration, the way it changes on the myocardium. And this is the effect of the solution of the problem at the cells level, say. And now you have the fluid dynamics. Fluid dynamics, you are solving a problem in the chambers, so in the ventricle, for instance, the left ventricle or on the atria, say. And here you solve the Navier-Stokes equations, the incompressible viscous Navier-Stokes equations in ALE formulation. What is ALE? ALE stands for arbitrary Lagrangian Eulerian formulation. Why is that? Because we solve typically fluid dynamical problem in an Eulerian framework and the solid mechanics in a Lagrangian framework. So you have to accommodate the two frameworks, and one possibility is to use this arbitrary Lagrangian Eulerian. This amounts to use the classical continuity equation, the divergence of u equal to 0 for Navier-Stokes, and you have to slightly modify the momentum equation. Instead of computing the classical Eulerian time derivative of the velocity, namely the acceleration term, you compute the ALE derivative on a reference domain, basically, that is used to retrieve at any time the actual domain, which is not the Lagrangian domain, because there are regions like this one that are fixed, right, that are prescribed a priori. So this is really a kind of hybrid representation. And you have to modify the convective velocity by subtracting the rate of deformation of the grid. So this is called the ALE velocity. You need a second equation which is there to compute the way the volume deform, every point in the volume, in the lumen deform, depending upon the deformation of the surface, which is the deformation of the myocardium, say. So we are using here an harmonic extension, and of course you have to adopt this type of to slightly modify the Navier-Stokes equation in order to allow for the computation in a domain that is moving. Here is an example of simulation. This is the left atrium. You see on the left the modulus of the velocity field, and on the right you see the vorticity. Actually, this is plot according to the Q criterion that I will use also later on. So you see in a physiological heart the way the big vortices are created from the four pulmonary veins that bring oxygenated blood from the lungs, and then you see the way the vortices are dissipated. Now we have valves, and we have to simulate the behavior of valves, and there are many different ways. You can go again by, say, very simple models that are based on just algebraic model to move the valves without any fine description of the valve themselves. You just move the geometry up to three-dimensional model of structural mechanics for the valves, or some intermediate approaches that are more affordable from the computational point of view, and also reasonably acceptable if you deal with the simulation of the fluid, if you don't necessarily deal with the computation of the stresses within the valves. So this is a kind of immersed approach. We're using the so-called RIIS method, which is the resistive immersed implicit surface. This amounts to perturb the momentum equation of Navier-Stokes by an extra term, and this extra term accounts for the motion of the valves, actually for the velocity of motion of the valves, and you have terms that account for, as you see here, the immersed surface of the valve themselves, resistance coefficient that we have to tune, then the thickness of the valves, a direct function, a direct delta function. You want that this, say, source term will only operate on the space occupied by the valve, and so you need to introduce this direct function that is distributed on the valve themselves, and of course you have to smooth it in order to treat it numerically. So this is the modification on the fluid part that we introduce in order to compute the action of the valves. And this is just one example. What you see here is the aortic valve, is the one that separates the left ventricle from the ascending aorta. Is a 3 leaflet valves, and the 3 leaflets open and close, I would say, almost instantaneously. So there is very fast dynamics, and this is one of the reasons why eventually we'll be forced to use time step that will be very, very tiny if you want really to follow the dynamics of what's going to happen. Now, this is a computational fluid dynamics model that is coupled with a zero-dimensional model. Also for the, say, the CFD model, we have to couple it with external circulation. So this is another possible model that we have to use. And again, I will not elaborate on that because of the time constraint. But as you can guess, what is also very critical is the way you actually match the 3D model with the 0D model. And basically, what we do is reported here on the right. The zero-dimensional pressures are passed to the 3-dimensional model, and they yield the 3D normal Cauchy stress tensor, which provides basically a normal boundary condition for the 3-dimensional model. And on each term, the 3-dimensional model, you compute the rate of volume variation of the cardiac chambers, and those information provide the 0D, the flow rate for the 0D model. Those are in wording the type of interface condition that you have that we actually use for accommodating the coupling of the 3D with the 0D. So here is one example where we have this 3-dimensional model coupled with the 0-dimensional model in action. This is the left part of the heart, and you see in the upper part the atrium and the lower part the ventricle, and here you see the ascending aorta. Here are the isocontours of the Q criterion. Q is, as you see in the formula on the left, is 1/2 the square of the norm of the rotation tensor minus the square of the norm of the strain rate tensor. So this is one heartbeat on the left heart. Now here is the way we couple the fluid dynamics and the structural mechanics. So we have the fluid dynamics equations, again based on the ALE approach. Then we have the structural mechanics, which is the elastodynamics systems that I've introduced before. Then you have the harmonic extension, and of course you have the coupling condition. This is the adherence condition. This one is the kinematic condition, and this one is the dynamic condition for the equilibration of forces. So what is missing is the myocardium perfusion model, and then our model will be basically complete. Myocardium perfusion means that the myocardium itself needs blood, needs to be nurtured by blood, and it takes blood from the coronaries. And now you have the big coronaries on the epicardium side. These are called the epicardial vessel, the epicardial coronaries. But then you have, say, tens of thousands of small vessels in the transmural myocardium. And how do we set up a model to describe the flow field in this very complex setting? We basically use a multi-scale approach. We use a Navier-Stokes equation, 3D Navier-Stokes equations on the epicardial vessels. And then we use a 3-compartment Darcy model, say a porous media description for the myocardium. And we have three different levels of size of coronaries in the myocardium. And we generate a surrogate intramural vascular network based on some optimized energy principle. And we end up with, as you see, the use of Navier-Stokes equations in the external, on the epicardium vessels, and then three different vessel compartments which coexist in the same environment, right? So at every single point, you can, or the myocardium can identify in the model the presence of the large vessels, the medium vessels, and the small vessels. So there's a kind of homogenization, mathematical homogenization principle, and this is the global system for the perfusion. Then you have the Navier-Stokes, and then you have the multi-compartment Darcy approximation, and then your interface condition set. So this is the last model, and this is first clinical validation. We see 9 different patients, P1, P2, P9, and for each of them, you see its own reconstruction of the epicardium vessels, and then you see the comparison between the measured perfusion map, which is obtained using a CT stress machine. So it's a stress test on the patient, of course, and here you find the computed perfusion map. And the comparison is quite good for all those cases. The error is below 1% on all the 9 patients. And this is quite reassuring because this test is quite demanding. I mean, you have to give to patient, to infuse the patient with a toxic drug, as very often happens, unfortunately. And of course, for some patients, this test can be particularly stressful and even sometimes dangerous. So here, the hope is to try to use numerical simulation to replace the test. Of course, it's a dream, but you have to start with a dream and then start with the first failures and then with the first success, and then hopefully to improve to the final step. So this is a big monster. This is the whole cardiac function model. You see all these components here. You see the active and passive mechanics, which is really acting as the driving factor of the whole heart functioning. And then you see the perfusion, the mechanical activation, the electrophysiology, the mitral valve dynamics, the aortic valve dynamics, and the connection with the rest of the circulation. And of course, you have the connectors. And the connectors are the interface conditions, namely the way all these blocks exchange information, physical information, one with the others. And this is what we can call the integrated heart model. So should we be able to solve this model, we will be able to have a simulation of the whole heart function. So let me just mention some of the main challenges here from the numerical viewpoint. We have multiple scales. We have seen them. We have lack of data. We miss initial conditions, boundary conditions, coefficients, fibers. We need geometrical nonconformities. We typically generate grades in an independent way for the different parts of the heart, for the lumen, for the muscles, for the valves. So you need non-conforming methods to accommodate all those grids. We will use splitting algorithms. We cannot afford using a monolithic method to solve all this, model in a single shot. We need scalable preconditioners because all the systems are stiff, and of course they are big nonlinear algebraic systems. We need to use model order reduction because often if you pretend being cooperating with doctors, we have to provide solutions, if not in real time, in a reasonable time. So not too unreasonable, but at least. So you have to use extensively model order reduction approaches, and you have to account for variability and uncertainty. Those are the major issues. So we have realized, or we're still in the process of realizing, a scientific library, which sits on the DIL2 finite element backend library. And this implements all the cardiac models, all the numerical approximation, and all the algorithms. And we call this library LifeX. We're also building up another library that we call PyFX, this is a library that is implementing reduced order models and solving uncertain quantification problems. So this is a research library again, and this is our frame where we are developing our models. So this is just a picture to show the way we split the different elements. You see, you can recognize the ionic model, the monodomain equation, the mechanical activation, the circulation model, the mechanics, the fluid dynamics, and the perturbation. And when you see a green arrow, it means that we are coupling those models implicitly when actually we go from left to right by at the new time level, say Tm plus 1. When you see a red arrow, it means that we are computing some of the models explicitly, some of the core models explicitly. You also see here these pictures of, say, cubic geometries, and they are there to indicate that we are using different grids for the different physical processes because the scales are different. And more typically, we use a very fine grid for the electrophysiology, a coarse grid for the mechanics, and the kind of intermediate grids for the fluid mechanics. And we're also using a staggered approach. Staggered means that we're using different time steps because the time scales are different. And again, the most demanding is the electrophysiology model, where we use a time step that is on the order of, say, 1/10 the time step that we're using for the other components. We have different type of spatial approximation. We go from Q1 to Q5. These are, say, polynomials of degree, say Q5 will be a polynomial of degree 5 in all variables on hexahedra. We use backward difference formulae of degree 1 to 3 of Runge-Kutta method for time advancing, and for the treatment of the linear terms, we use both semi-implicit and implicit terms. We use for the fluid dynamics part, we use typically Q1 plus, so equal order interpolation plus SUPG stabilization with variational multiscale and the largety simulations. For the solvers, well, we use linear algebra backends based on Trilinos and Pezzi. We use scalable preconditioners. We use algebraic multigrid, BDDC, domain decomposition, additive Schwartz, or physics-based preconditioners, say. And as I was saying before, for the electrophysiology, typically I use 10 to the power 7 degrees of freedom with a delta T, which is of the order 10 to the power minus 5. And this takes typically 6 hours on a small, say, cluster with 100 cores. Electromechanics, we are a bit more tolerant in terms of, for electromechanics, so we need 24 hours. For the fluid dynamics, 24 hours. These are typical, order of magnitude, right? And for the complete integrated model, we estimate order 100 hours for a single heartbeat. So it's very demanding. So you understand why we need to use reduced order models to solve the forward problem, the one that we have seen before. But even more if we want to use uncertain quantification, because then we have to solve iterate, and for every iteration you have to solve the forward model. And we like to address both epistemic uncertainty, which is due to lack of knowledge or experimental error, and aleatory uncertainty, which is due to stochasticity and the variability between individuals, for instance. So here are some examples. Of course, I have very little time, and I'll be extremely quick on that. But I just wanted to give you an idea of the type of approaches that we're actually using in terms of reduced order models and also for addressing uncertainty. Here, we want to approximate activation patterns with different type of fiber distribution and electrical conductivities. So we want to explore variability, and we use the local reduced basis method, what is called the k-means based. So we are using local reduced basis methods, and this is just to give you so the k-means clustering, And this is just to give you an idea of the potential saving that you can realize with respect to using the full order model. Right? It's the speed up in the order of 35 times to achieve a relative error which is of the order of 10 to the power minus 2, and with a memory storage which is really, I mean, you get a very substantial advantage. So with an error which is between 1% and 2%, the speed up is 35 times in this specific case. We solve it. We use it also for solving the inverse problem. We go for measurements, for instance, the electrocardiograms, to try to reconstruct the electric potential on the epicardium. So it's a PDE constraint optimization model. We use NC samplings with gamma filters and use neural networks. And again, we are really interested in getting substantial advantages. We use artificial neural network together with physics-based models, and we use that for speeding up the computation and for devising reduced order models, say. So the idea is always to combine high fidelity models with reduced order models in many different ways. Here is the purpose is to compute the model that produces the active force at the cell levels. As you can see, of course, I had no time to describe the details, but there are references, and so you can find details in the references. Or of course, you can contact me. I can send you material. But this is the typical type of advantage of gain that we have: 400 times speed up for the fourth generation model, and on the global electromechanical model, 10 times the speed up, and the 100 the factor of memory saving is order of 100. So it's really quite important. This is yet another issue. It's applied to another possible, say, combination of full order model and reduced order model based on deep learning for the electrophysiology. And here is just the schematic picture. We actually start from full order model, and we have a convolutional autoencoder, which is made of convolution encoder and the decoder. Then we account for the parameterization and use a reduced order model for that, and we end up with a deep learning reduced order model for the electrophysiology. And here again, you have an idea of the advantage. Say the full order model takes 2 hours, and with this approximation on the online phase, it takes less than 1 second. Those are further combination between, say, full order and the reduced order models based on the use of artificial neural network or deep neural network, and in this case, this is to solve the inverse problem of the electrophysiology. So again, here you have a picture of the potential advantage that you have, and again, without this type of say combination or boosting of computational time by the use of artificial neural network, of reduced order model, or deep neural network, it would be, I would guess, basically impossible to address real clinical applications. I've not had time to show them, so we stop here. But to address clinical applications, you really need to end up with those reduced order models and this help from artificial neural network in order to be able to account for the variability and the uncertainty. And I would like to stop here. And thank you very much for your attention. And
thank you.
I'm glad to take any question.
Thank you so much, Alfio. It was a great talk, and we will open to the audience for any questions they have. So we do have some questions from.
Unfortunately, I'm not able to see the chat. So if you
I'm going to
open the microphone, if you can help me, please.
I'm going to read it to you. Well, the first one is rather not a question. It's some comments from Rob Blake at Laurence Livermore. Hi, Dr. Quattroni. Glad you enjoyed the LDRDM method. I have some modifications that make it work well for the papillary muscle as well.
Oh, great.
So Rob, if you want to speak out further.
Yeah, I was glad to see my name in the credits down below. I was one of the authors on the rule-based thing. There's some simple modifications I can talk to after. You just modify one of the Dirichlet boundaries, and you can get papillary muscle fibers as well.
Oh, very good. Thank you. Or you can send me.
Yeah, I can send you something
by mail and information. Yeah, thanks. That would be very helpful.
Okay, awesome. Well, and Martin Berggren, he asked about the electrophysics model. Looks like a diffusion reaction equation, but he was wondering about the picture suggesting transport. Rob has answered that question, but I guess Alfio, you can revisit that question again.
Let me see if I can get the model here. This one, do you see it?
Mm-hmm.
Mm-hmm.
So maybe I can go full screen. See if I can go full screen. Okay. This is a monodomain equation. So the question is about the reaction diffusion problem that is governed this equation, right?
Mm-hmm.
So what is the question exactly? Sorry.
The question is, the picture suggests the transport. So how is that? I mean,
the picture suggests
the transport.
The transport term.
The transport looking, picture.
It looks like advection, but it's reaction diffusion. And how can that be possible?
No, we don't have transport. No, this is not the transport. This one.
There is no advection terms in equations.
No, there is no advection term. No, there is no advection term. This is the time derivative, and this is the elliptic part. So it is the divergence of the conductivity tensor time the gradient of u. So this is a kind of Laplacian, say generalized Laplacian, and this is a source term.
Exactly, but one of the picture you showed suggested some transport.
The picture, you mean the simulation?
Right.
This one?
Right.
Yeah, that looks like a transport term, but Robert Blake already answered the question.
These are actually internal layers. So you are right. I mean, it has the behavior of a diffusion transport equation with tiny layers, but indeed this is the internal layers that are generated by the specific structure of those equations. There is no transport term.
Okay. So next question is by Rob again. Can you talk a bit more about what you are doing with a reduced total modeling?
Well,
I think
that actually got answered by the later things. I actually had a general question in the last 3 minutes. Where do you see this going in the future? Because you've presented a very, very, very complicated multi-physics model. Do you plan on introducing more multi-physics into it? Do you plan on going more reduced order method? Or do you plan on going towards clinical applicability?
Yeah.
Which direction do you want to move?
Yeah, that's a very good question. Thank you very much for asking this question. This is indeed a question that I'm asking myself very many times, and I give myself these answers. I think I'd like to go in two different directions. The first one is just the direction of bringing more knowledge into the subject, if possible, of course, meaning that I like to have a basic integrated heart model that is capable to describe the function of the whole heart in all its components. And I try to convey this message by showing you all these, different core models and the way they're coupled together. Of course, this has no limits in the sense that you can improve the model every time. As far as you better understand biology and physiology, then you can improve your model. But already this model is, I think, good enough to address clinical issues. And this is the second part. So when you address clinical questions, we will almost never use the full model. That's too much. This is too rich, if you want, right? We try to specify, to use subcomponents of the model to address specific questions. For instance, this is an example. To address arrhythmias, basically the fluid dynamics in the ventricles are irrelevant, almost irrelevant. They might be relevant in the atrium because of the auricula where you have recirculation. But let me say, generally speaking, when you address a problem of a clinical relevance, we try to understand what is important and what is less important. And in the overall model, we disregard, we drop what is not so important. So these allow us to go into the reduced order model part. When we isolate the components that are useful to address a specific application, then there we try to take advantage of reduced order models, in particular to address uncertainty. So somehow we scale down the complexity when we address clinical applications, because otherwise that would be simply too demanding. So, and this is the same also for, fluid dynamics. When, for instance, in this case, we address a problem that has to see with the myosectomy, and in this case, the electrical field does not play any role. So you really account for the mechanofluid part and disregard the rest. So there is a component which is, let me say, of academical interest. We try to improve the knowledge in the field, and I want my model to be as inclusive as possible. And this might be extremely expensive, computationally speaking. But I want to be able to provide pictures, simulations, quantitative information that would be otherwise impossible to have with the standard imaging tools that we have nowadays. So this is one goal, and the other goal is go into more specific questions from the clinical side. And for that, I really have to lean up my model to the limit, and to limit it to the most important components, and to use very extensively reduced order models and say deep learning or artificial neural network in order to provide solutions in a shorter time, certainly compromise in terms of accuracy.
Thank you so much. I do have one question. You mentioned the PDE aware, the deep learning models. I'm guessing you have already applied such methods
yes.
in your project, and if you can give us some more details about
this is one where we really combine full order model with basically to compute the snapshots, right? And then we train the network with this snapshot. But this is another one. This is another example where you are actually embed the information from the physics from the models into the neural network. This is there to solve an inverse problem. As you see, we start from data, and those are on the left-hand side. Those are the ECG maps, and we use a neural network to end up with a model, and then we use the PDE model, which is the one that combines the electrophysiology in the myocardium together with the Laplace equation in the torso. We use this model to basically set up the cost function and to train our network, and then we return the electrocardiogram signal with this help, basically. So what we try to do here is to solve the forward at the inverse problem electrophysiology with it's a kind of physics-informed neural network. I think the name that was given in the first paper is not exactly the same, but it's basically about the same. I mean, we really try to take advantage of the physical models in order to set up to realize an artificial neural network model, say.
Right. I totally agree that we need to incorporate the first principle into the deep learning models we have. I do think that a lot of people is going to do more research on those.
I think according to our recent experience, this is really one way to go.
Right.
We really see that in many problems, really. I mean, if you set a compromise in terms of accuracy, it's always a matter of trade-off between computational time and accuracy, right? When you deal with such complex models. So if you really play with this in a suitable way, and you set up the accuracy that is mandatory at the clinical level, and you want to fulfill that accuracy, and then we try to be as efficient as possible, then combining a physics-based with the data-driven models, it's certainly, I'm not saying that it's the only way, but certainly it gives us a very important advantage.
Right, totally agree.
I just wanted to add as well, I have some unpublished stuff. We have a giant database of simulations and reconstructed simulations, and we have some stuff that shows that given just an ECG, we can actually reconstruct like an equivalent of kind of an iconal distribution of what's happening everywhere inside the heart.
Okay.
So, like, just not even having to put any models in, just go straight from ECGs to what's happening inside the heart.
All right.
Showing it a million simulations.
Okay. And using the Econal model?
No, equivalent to the Iconal, but not using the Iconal model, just using a
I see.
network.
Okay, so it's purely data-driven then?
Yeah.
Oh, okay.
Okay, we do have one more question from Long Chan. He said, thank you for the talk. Can you elaborate more about uncertainties? For example, you have talked about epistemic and aleatoric uncertainties. Which is more interesting in medical practice?
Well, I think that what is important here is well, first of all, in medical practice, you have uncertainties everywhere, right? I mean, you have uncertainty from the data characterizing the patient himself or self, say, the individual. So the data that characterizes the shape, because of course you have errors in imaging acquisition. You have very lack of information about the fibers, for instance, fiber distribution. You have very lack of information about the mechanical characteristics of the tissue, the mechanical tissue. You have uncertainty on the boundary condition if you have isolated systems, and those are initial conditions. How do you say start your simulator? So you don't have initial data. You are very far from the beauty of the PDEs, where you are given a boundary condition and the initial condition, the forcing term, and the material coefficient. You are very far from there. So those are very important. Uncertain elements that you have to play with. And one possibility is to use those uncertain elements and try to introduce probability space. You represent them in a probability space, and you try to see the way your forward model propagates these uncertainties onto the desired solution, the output. This is one way. The other way is when you start from measurements and you want to reconstruct in an uncertain way, for instance, the coefficients or the fiber distribution, again in a probability space, not in a deterministic way. So those are two elements. And then you have the inter-patient uncertainty. You know that we are all, each of us, different than everyone else. And what is the dream here? The dream is that one possible dream is to have atlas of people of different shapes of heart, for instance, and then trying to move from when you have a newcomer to try to exploit the previously available information and try to not to extrapolate but to produce a result on the basis of the previously computed results in again in a certain way. So you have intra-patient and inter-patient uncertainty, and then we like to eventually address with all these cases. Of course, it's a kind of gigantic effort, but so far we have some examples, some instances of applications where you can, I mean, those are really proof of concept. You really want to see that, to prove that you can set up a mathematical paradigm, say, mathematical setting that in principle allow you to treat with all those uncertainties. But again, the issue of producing results within a tolerable accuracy with acceptable computational time is really a big issue, it's really a big challenge. So it's a proof of concept, basically.
Okay. We have one more question from Martin. Did you use any LES model for fluid?
Yes, this is for the fluid dynamics. We use a dynamic LES model. We are actually using a Q1, and see if you can restore it, but there is no detail here in this presentation. Yeah, we have Navier-Stokes equations in the ventricles and in the atria. We use Q1 for the velocity field and Q1 for pressure. So bilinear or trilinear elements, actually, because we are in 3D. Trilinear elements for velocity and pressure. Then we have SUPG stabilization, which means that you are adding residuals to the continuity equation and to the momentum equation. And then we use LES in a variational multi-scale framework. It's a dynamic LES. So this is pretty much on the line of what, say, Tom Hughes and all his schools say has been doing in the past 20 years for separating the scales in a problem which is not turbulent, because this problem is not actually turbulent. I mean, the fluid dynamics in the ventricles does not at least in healthy patients does not heal the turbulent flow, but is a kind of permanent transition towards turbulence, because there's not enough space and not enough time to develop to produce a fully developed turbulence. So we have a transition to turbulence, and that's why we are using actually the large area simulation, say turbulent models.
Thank you, Alfio. I do not see any more questions. Well, that doesn't mean you cannot ask questions. If you have questions, unmute yourself and ask questions. You're welcome to do so. Well, if not, let's thank our today's speaker, Professor Alfio Quattroni. Thank you so much.
Thank you, Young-Soo, and thank you, everybody, for attending my talk.
Okay, great hosting you today. Just for the announcements, I believe, I have to check, but I do believe that we have another DDPS seminar next week. So please stay tuned. And until then, stay safe and see you next time. Okay, bye.
Bye, have a good day, everybody.